In this video, I'm going to show you how you can use features from different geometry representations to create fields that ultimately go on to be used to drive lattice properties in field-driven design. In the first part of this demonstration, I'm going to use the model that you see on the screen here. This model is useful because it has lots of different sections that we can apply different lattice effects to. We'll be able to show these on screen at the same time so you can compare and contrast the different lattice types and the different field-driven gradient effects. If we explore this model a little bit more, first by isolating the inner ring, you can see that we have a frame that holds lots of different plugs, and each plug can be converted into a different lattice type. Here I've shown the center plug, and what I'm going to do is apply a surface lattice to this section. I'll change the visualization quality to high so we can see more detail. And I'm going to apply a Schwarz P surface lattice. The effect I'm going to show is best shown with a double lattice. And I'm going to lower the density so it's more of a thin-walled structure. I'm now going to apply a field to the unit cell size, and the unit cell size is measured as a count across the largest dimension of the shape. Here I've selected an arc or a circular line that's a reference from the BRep geometry. I can then pull in these handles so that I can size the inner and outer extents of the field-driven effect. I align one with the inner diameter of this center plug, and I leave the other at the center so that the effect is applied right the way across the radius. Setting these handles gives me the minimum and maximum distance that I need to specify the gradient. The next step is to rescale this. You'll notice that I've left the rescale checkbox ticked in the field context. I now need to say how the minimum distance and the maximum distance, which are 0 millimeters and 19 millimeters respectively, map on to different cell sizes. The minimum cell size in X corresponds to the minimum distance value, and the maximum cell size in X corresponds to the cell size at the maximum distance. If I word this differently, this is like saying I will have 4 unit cells at the center of this section, and I will have 16 at the periphery, and you'll notice that the cell size smoothly varies. I've now changed this to 8 to make the gradient less severe, and once I'm happy with the visual appearance or the engineering performance of this design, I can accept those changes. And as I view this from different angles, you can see the wonderful effect that's created as the gradient varies smoothly. And this is not something that's possible when you tile unit cells in the traditional sense by using patterning operations. This is something that can only be achieved with field-driven design. I'm now going to reveal another of the plugs in the design, and we'll apply a different effect there. We can see this plug here, and this time I'm going to create a strut lattice. I'll select the part I wish to apply this strut lattice to, and you'll notice that there's nothing visible at first, and that's because the strut diameter is too large. So I reduce this to 0.5 millimeters, and I'm then going to choose the Kelvin cell strut type. To fit it better into the geometry, I'm going to use a cylindrical coordinate system, and this will mean that the lattice follows the contours of this cylindrical shape. I'll now update the unit cell count along the X or radius direction, the theta and the Z direction to get a more representative lattice geometry inside this plug. When we view this from above, you can see how this follows the contour of the shape. I'm now going to apply a field-driven effect to the strut diameter. The default is the Z equals 0 plane, and this is not what I want, so I deselect this, and I select this arc from the BRep reference, and that gives me two cylindrical handles that I can use to set the extents of the input range, the minimum distance and the maximum distance. So I'm going to snap this to some existing geometry that is convenient for this plug, and you'll notice it picking up the snapping points denoted mid in this video. This will accurately set those input ranges, and I'm now going to choose to clamp the values for the output so that they cannot go above or below the minimum or maximum strut thickness, even outside of this range. So the minimum strut thickness I'll use is 0.5 millimeters, and the maximum is considerably higher than that, and I'm going to play with this a bit until I get an effect that I'm happy with. Here I try 1 millimeters. I think I can reduce it a little bit more on the minimum strut thickness, and that looks like something I'm happy to work with. So if I zoom out, we can clearly see the gradient travelling radially, and that is how we introduce another field-driven effect from BRep reference geometry. Let's have a look at another example. This time I'm going to create a planar lattice. So this is a 2.5D geometry, almost having a direction of extrusion, if you will. And for this particular case, I'm going to use the diamond type. Once again, I'm going to use the cylindrical coordinate system so that it conforms to the shape of this plug, wrapping around the geometry. Let's just change some of the width and thickness values so that we get something representative to start with. And that looks like a good start. I'm now going to apply a field-driven effect to the thickness. This is the wall thickness of this lattice. I'll create a new field, and this time, conveniently, the z=0 plane is a very good reference for what I'm trying to achieve. You can see the two planes here that bound the field-driven effect. They're in the right position by default, and so all I need to do is set the minimum and maximum thickness as I rescale the values of distance into thickness. So the minimum thickness I'm starting with is 1 millimeter, and the maximum is 0.5 millimeters. And I know those sound like they're in the wrong order, but it's not a matter of specifying the minimum thickness. The minimum thickness is the thickness that corresponds to the minimum distance in the input range. Likewise, the maximum thickness is the thickness that corresponds to the maximum distance in the input range, and that is the best way to think of this mapping. If we look from above now, we can see that the lattice is quite open at the top and linearly becomes closed, or the diamonds become smaller as we travel down through the part. And this is a nice way of using planar features to drive a field-driven effect in lattices. We'll now move on to a different example where we'll use points or spherical surfaces to achieve different effects. I'm now going to show you how we can use points or spherical BRep surfaces to define gradients that are used in field-driven designs. And in this example, I'm going to show that applied to the density of a lattice. The process starts by importing this body here, which is a spherical body that's been trimmed. And I've also created a construction point at the center of these spheres. I'm going to include a surface lattice in this case. I could choose any of the lattice types, but a surface one will work well. And a Schwartz D gives an interesting effect in this example. I need to change the coordinate system to be spherical, and just check by clicking the Locate Origin button that the origin of the lattice is indeed on that construction point. I'm now going to change the unit cell counts along each of the spherical dimensions, x, which is radius, theta, which is one of the rotational directions, and phi, which is the second rotational direction. Once I'm happy with the way the unit cells sit within the body of the lattice, I can then start thinking about field-driven design, and in this case I'm going to apply it to density. So I'll create a field, and by default this takes the z equals 0 plane, so I'll deselect that. I'll now select point 1, and this will throw up two very useful visual guides that allow me to set the spherical gradient. By bringing the original BRep back into view, I have the ability to snap these spheres onto the BRep construction. You can see the endpoint highlighted there. And that lets me set the min and max distance in the input range precisely. All I need to do now is to decide how I want to set the minimum density, which maps onto the minimum distance above, and the maximum density, which maps onto the maximum distance above. Once I'm happy with these, I can inspect the model, check that everything is as I'd like it to be. I have a higher density on the inner spherical shell and a lower density on the outer spherical shell. I'm happy with the way this looks, so my final touch will be a very gentle Laplacian smooth. I'm even going to take the strength of this down to 50% of its full strength, and that will clean the model up nicely so that I can continue downstream processing. Let's just have a look from some different angles and satisfy ourselves that the design is how we want it to be. And that is how you introduce a spherical gradient into a field-driven parameter on a lattice design.